I don't want to miss a single thing on this. So let's just be clear. You had 4 assignments. This is, let me say this clearly. This is Monday, October 22nd. Candy Day's almost here. 2018. Like, how do you not know that? So Monday, October 22nd, 2018. And on Friday, I issued you, and you were assigned Chapter 7, Section 4, to read over the weekend and to complete. You by Thursday, you were told you had to finish 4 assignments that were out of the book. All right, 4 assignments out of the book, one of which was a lab that we will do in class. The second assignment was a video that was something like a minute and a half long. You're supposed to watch and take some notes on. And 3 and 4 were 2 written assignments, which you have just gotten. You've just gotten physical samples of this today, although you had these available since Friday. One of the assignments, one of these is actual notes. It's Cornell notes, Cornell guided notes. And the other one is a kind of a concept wrap up. And you were asked, somebody asked me, do you have to create the foldable? Yeah, you have to create a foldable. Yeah, there's a whole foldable section. Make a 3-pocket foldable from an 11 by 17 sheet of paper as you read, record information about cellular transport and on quarter sheets of notebook paper and store them in an appropriate pocket. Now, obviously 11 by 17, you may not have that kind of paper around, so I'm going to try to find that paper for you, but if I can't, you can create a foldable and make the squares smaller. You can take an 8 by 11 sheet and fold it on the side, put it on the side, make a foldable this way, and put pockets on it. You can construct that, and you can make one for diffusion and one for active transport. And you should have read the chapter already, so you should already know what I'm talking about. And another one that says for passive transport, right? And then you can put your little cards, little notes. You can put stick-it notes or some kind of notes in here. So we can adjust this so it's something that you can do at home. So this would be an 11-inch by 8-inch. What's 11 by 8? 8 by 11. What is that? A sheet of paper is 8 by 11. And then if you fold it, so you lay it on its long side, you fold it into 3 parts, right? Then you take another sheet of paper and you staple. You just staple out the 4 corners of each of and creating a what? A pocket. So there's your 3 pockets. You can label, right? And then you put your little post-it notes for the various answers into each pocket. Now, what I'd like to see is actually you go ahead and do it in color, so we can have like one color, one post-it note that's red, another that's blue, and a third that's yellow, and a fourth that's green. Whatever, for whatever characteristics you want. That would be nice.
What's the middle one?
And you can even, if you're going to use post-it notes, really, you don't even need the pockets, right? You could just divide into a sheet of paper into 3 sections, put a line down, and then stick post-it notes on there, right? So there's a bunch of different ways you can do the same thing. The key is that you want to create this kind of summary. It's on page 80 of the work, and that's people keep asking me if that's necessary, and I'm going to say yes, it is. All right, so let's move on then. let's go over the content now. Now that you've read the chapter for homework, you've started writing. Some of you told me you tried to write it in the document. I warned you that writability using the ebook, as far as it saving or whatever, I'm never confident on that. So I would either download that assignment and do it on your computer, or get the printed copy from me, or print it yourself in the hallway. So it's like a bunch of different options that you can choose. You can print in the library, right? Don't you get a certain number of free copies at the library?
No.
Yeah, you do. Please go to the library. Yeah, when's the last time you've been in the library?
Like 2 days ago?
And they don't give you any free copies?
No, it cost 10 cents.
You used all of the free copies, ma'am.
Yeah, that's why.
Lakewood Library fucking.
All right, so go to different libraries, you might get different deals. And of course, you have printers in the hallway when they're working, and they generally are. They have them in the hallway ready for you to print. So there's really no excuse, right? These assignments, several people asked me, well, there's no place to, because the other kids, the kids that came back to get these, because I told you to come back and get these, kids that came back and got them at the end of the day, they're already done with these, and they want to know where to upload them. So when you're feeling like, oh my God, I have so much work to do, it's too much. You see, when you get ahead of the curve and you get things done early, then you're one of the kids that's sitting back and relaxing, saying, man, I'm ready for the next step. All right, so that's the work we got to get done. Let's go ahead and start going over the content then. So we talked about cell membranes, and we'll get back to the composition of the cell membrane, but the bottom line is we know that the membrane has, in general, this going on, right? And we know that the membrane, at this point, we've learned that the membrane has hydrophobic and hydrophilic sections. At this point, I would hope that everybody knows that you have the lipid layer, which is here, right? And then you have the hydrophilic section, which is out here, the heads on both sides. And that this acts as a barrier. What it's called is a semi-permeable membrane. In other words, it allows permeable means allowing things through. Something that's permeable means it allows material through. All right, so it allows material through. So semi-permeable, what do you think semi-permeable is going to mean?
It doesn't
Allow some.
It stops some things from getting through, allows some things through. I like these ideas. Let's go ahead and put those definitions down here. So somebody said allows some things through. And somebody else said prevents some things from getting through. And which one's true? Both are true. It allows some things through, but stops other things from getting through. So both of these, membranes do exactly this. They allow some things through, and other things they don't let through. Well, what is it that they let through, and what is it that they don't allow through? Well, we have to think about what the membrane's made of. The membrane is made of this lipid layer, hydrophilic. Remember, we have to think about what a cell is made of. What is it that you have this cell? If I draw this line, this is the membrane. We know, everybody understands that the membrane looks like this. Everybody's good with that, right? So when I draw a single line, I hope everyone in their mind sees, my hope is at this point, when you see a line around a cell like this, and you know it's a membrane, that what you see in your mind is this. I hope by this time, after we've built a 3D model, after we've drawn it 100 times and we talked about it, right? We've drawn each phospholipid in your study guide for the last test. If you remember, you had the phosphate head, right? The lipid tail. This would be the saturated fatty acid. This one is the saturated fatty acid. And this one would be with the double bond, unsaturated fatty acid. And this, so it has like a little kink to it, right? Right? Do you remember that? I hope, yes, maybe, sort of. All right, so that would be your kind of phospholipids. And so when you see this membrane, I hope you don't see like this line. I hope you see a membrane in your mind. And at this point, you should know that outside the cell you have what? What is it? Water on the outside, and there's water on the inside. So water is a solvent on both sides of this membrane. So what do you think is the one thing that and so we know the other saying, we have this saying that says that like dissolves like, right? Like dissolves like. So what kinds of things are dissolved in water? If like dissolves like, what kinds of things are dissolved in water? What do we find in water? Whether it be blood, because blood solvent is water, right? Or it's inside the cell, or it's in your glass of water. What kinds of things are dissolved in water?
Stuff that's hydrophilic.
Things that are hydrophilic. So hydrophilic substances or polar substances, right? Polar or hydrophilic substances are the things that are dissolved in water. Is everybody okay with that? We're good with that idea? So what kinds of things are polar or hydrophilic? Well, one, of course, water. Water is polar, so water is dissolved in water. Well, water is dissolvent, so what other kinds? So what are things that are dissolved in water? What kinds of things have we talked about? Salt, excellent. So we got salt. So can I just use another word instead of salt? Can we say ions? Is everybody okay with the word ions? Does everybody in here know what ions is anybody confused about that? If you're confused about it, now's the time to ask. What are ions? Yeah, you're confused? Okay, good. I'm glad you said something. I'm glad she said something. So ions are charged particles. That's all you have to know. Now, you could know more. You could know that there are atoms that have an imbalance in their protons and electrons, that they have more electrons or less electrons than they do protons, and therefore it gives them a charge. You can know that. But they're basically particles that have a charge. So they either have a plus charge or they have a what? Negative charge. And they can have more than one. They can have a +3 or -3, and it can be more than one atom or single atom. All that is true. Molecules can be charged. Is that clear? But so can atoms. Atoms and molecules can be charged. Water is polar. Now remember what the difference is between polar and charged particles? What do we mean by particles? We mean small things, right? So salt is made of ions, 2 ions, one positive, one negative. When we're talking about molecules, they can be ions as well. There are polyatomic ions, so there are molecules that are ions. But there are also a lot of polar molecules. And water is an example, one. And remember, we drew water out. I'm going to go ahead and draw water out again. And remember, it's the epitome. I remember that partial positive and partial negative and partial, right? So that the oxygen side has a what? What does the oxygen side have? A negative, a partial negative, partial. I keep using that word partial, I mean it. That's the big difference between charged, right, and polar molecules. What's the difference? The difference is that the charged particles have a full charge. The polar molecules only have what? A partial charge. They have a partial charge, and there's a partial charge at each side. Right? So that's what makes them polar. There are two sides to that. And we talked about that with DNA. We said that was important for DNA. And you were tested on that, weren't you? I was expecting that you'd know that based on the exam. All right, so we're good with this so far. Is that right? All right, so these are two really big ideas. There are actually two or three really big ideas. Let's go over them one more time here. First, like dissolves like. So polar dissolves polar, and nonpolar dissolves nonpolar, right? Or hydrophilic dissolves hydrophilic, and hydrophobic dissolves hydrophobic. We're all understanding that? That also the opposite's true. Hydrophobic repels hydrophilic. Just remember, bless you, what we started this whole conversation with. Oil and water do not mix. Oil and water do not mix. It's a very simple statement, right? And we know that oil is a fat. Oil is a lipid. So this lipid will not mix with this water. Is that clear? Then we said that these things that are called ions, they're charged. They get dissolved by things that are polar because the charges all align, and they can attract each other, right? If it's a positive charge, what could water attract? Which side of water is going to attract it? The negative side. So oxygen is going to surround, the oxygen side of the water molecule is going to surround the positive, right? So what you'll get is something that looks like this. Positive in the center, and then you'll get the oxygens surrounding it. Of course, the oxygens bring with it the hydrogen, which are covalently bonded, right? They can't help. So water, that's how water dissolves things. Look at it. It separates it like sharks, if you like. Yes. And if sodium chloride, the sodium is positive and the negative is chloride, what happens? What's happening with the chloride? The negative. What's pointing towards it? The hydrogen. And the hydrogens then all point towards. And you see how water can separate sodium chloride? How it can dissolve it? It can take, because it's polar, it can take and separate, we call hydrate, the ions. So the ion positive charge gets separated from the negative charge and dissolves into the water. They're suspended in the water. You just can't see it. Are we clear on this? So that's how polar dissolving things work, right? So they're floating around in the water. You have a question?
So if it's dissolving something negative,
the oxygens are going to point towards it, right? If it's positive, the oxygens are going to point towards it.
And then if it's negative, they point away from it.
Yeah, right? Because what do like charges do? Repel. And even a partial negative is going to be repelled by a negative, right? They're magnets. This is all about magnets. Just think magnets. Is that clear? Yeah? You played with magnets. You know positive. This is all the same force. Electromagnetic force is what we're talking about here. Are we good? Remember, a force is a what? What's a force? From middle school. Say it. I heard it. Push or pull. That's all a force is. Somebody talks about a force field. It's just something that pushes or pulls. That's it. So So in the case, in here, the oxygen pushes away from the negative, but the hydrogen gets what? Pulled towards it. So they get surrounded, and when they get surrounded, they get separated, and when they're separated, they're in solution. They've been dissolved. All right. So we got that. We got like dissolves like. We got hydrophobic. We got hydrophilic. We have polar. We have ions, right? Charged, fully charged, partial charged. We're all good with that? All right. So now let's talk about transport. So the cell has a problem. The cell has this really big problem. What is that problem? Anybody know what the problem is?
Transport.
Transport. How do you get something that's... So you got a bunch of salt out here. He's not only is he very smart, you're right, but he's also someone who did their homework. Salt, and you have a bunch of sugar. Sugar, by the way, dissolves in water. You know that. So you know it's what? Polar.
Polar.
Right? Hydrophilic. And you know salt dissolves in water. It's actually ionic. Right? We're good? So we know those two things are true. But there's all kinds of other stuff in here. We got what kinds of salts are we talking about? By the way, I know you're used to table salt, right? That's what you think of. But you have to think about a lot of different things. So salts are actually any metal or non-metal bound together. So any calcium, any sodium, any chloride, any lithium, any I don't know what else, fluoride, any potassium. These are all things in your blood.
You said any what they bond together?
A salt is any positive and negative. So sodium is a plus and chloride is a negative. Those two together form sodium chloride. You know it as table salt. Calcium can bond with chloride, and this is what you know of as rock salt, right? There's at least one of the components of rock salt. So there's a lot of salts. Seawater actually has a lot of different salts in it. Dissolve, a lot of ions dissolve. These can all combine. Look, anywhere there's a positive and a negative, what can happen? You can get potassium chloride, sodium chloride, lithium chloride, calcium chloride. Metals have a positive charge, non-metals have a negative charge. Yeah.
Isn't it true that like table salt, if you eat, like how it's bonded together, if you eat any of them separate, it should die?
It's complicated. If you put sodium metal into water, it pretty much explodes. It releases a lot of energy very quickly. So if you tried to eat sodium metal, which is pure sodium, without the chloride, then it would probably burn a hole in you, right, and hurt you very badly. In fact, we used to have sodium metal, and I got rid of. I said, wait, I don't want it anywhere near me. I don't need that stuff. This stuff it's actually stored in oil, because if it touches water, what we just described is it going into solution happens so quickly that there's a lot of energy released. So it's complicated. All right, it has to do with a lot of chemistry. You have to wait until you're taking conceptual physics or chemistry. All right, but in any case. We're moving on, yeah.
What does the K and the Na and the Li stand for?
Potassium, lithium, sodium, calcium, chloride. Yeah, or chlorine.
So, when you make salt, it has to be one positive, one negative. It can't be two positives, one negative.
Yeah, it's one positive, one negative. These are not molecules. People think of them as molecules, but they're actually ionically bonded. Ionically bonded compounds are not, we don't consider them molecular bonds. They're not covalently, they're not sharing electrons. They're just a fully charged, what happens when you have two fully charged things, what do? They stick together. They're just stuck together. They're not sharing electrons. They're easily separated. They're much easier to separate sodium chloride than it is to separate water, for instance. Right? So even though they have a high melting point because of the intermolecular bonds that they form, when it comes to the molecule, there's no molecule, or it's not really intermolecular bonds, they're metallic bonds, but in any case, the bonds, these things are not as tightly held together as oxygen and hydrogen are in water. It takes a lot more energy to separate oxygen and hydrogen than it does to separate sodium and chloride. All right. So anyways, these form kind of a lattice structure or matrix. And that's what you see as salt. You'll see a cube. When you see a salt cube, you'll see what it is. If you look real close at salt, you put it on your hand and look close at it. They're little tiny cubes. And really they're just millions of these sodium and chloride atoms all oriented to positive, negative, positive, negative, positive, negative, positive, negative. Yeah.
So those two things in the salt that's in our blood too?
Yeah. All this is in your blood. And sugar too. So it's in the blood, but what does it have to do? It has to do what? Well, it's broken down, so it's in solution in the blood. It's floating around. What's it going to do? What does it need to do? Yeah.
I don't know exactly, but it like performs a certain function in the cell.
You're right. It does perform a certain function in the cell, but if it's in the blood, think about it. If you're in the blood, it's in the bloodstream. Here's sodium. Here's chloride. Here's calcium, 2+, right? Calcium is 2+. Here's salt. Those are salts. What's this thing here?
What?
Here's sugar.
Oh, that's the sugar.
So they're floating around in the blood, right? What do they have to do? They have to get into the cell. I heard somebody say it. They have to get. These are your cells here.
I see.
These are the cells that make up your bloodstream, your blood vessels, right? And then there are cells that are in your bloodstream, right? Kind of a little red blood cell here drawn badly, and then a white blood cell. So you have a nucleus, endoplasmic reticulum, rough and smooth, the Golgi body, nucleus, nucleolus, ribosomes, mitochondria, and that's repeated over and over and over again. So I guess my question is, how is all this stuff? And by the way, this is not to scale, right? If we were going to look at the scale, these things would not be like this. What you would be seeing is these molecules would be like that, right? Maybe sugar would be like that. Does that make sense? These are all dissolved in water. What do you have to do? Yeah.
Well, I was just gonna say that the protein accepts all of this stuff and it makes like the sugar and the sodium.
Very good. I like your thinking, but I guess my question is a little more basic. You're thinking more advanced. So my question is, what is it we have to do with the sugar, the sodium, the chloride, the calcium, all the nitrogen, the new proteins, the amino acids that are in the blood, right? All those molecules, the hormone. What do we have to do with this that's in your blood? What is the whole reason? The oxygen. You have oxygen in here too, right? You have O2. You have O2 in here. And in here you have a lot of CO2. Somebody go ahead and say it. I don't want to look out and call upon you. I don't want you to say it. What is it you need?
Transport
You need to transport it. Transport it where?
into the cell.
You have to get it into the cell. So it's here in the blood, but what do you have to do? You have to get it out of the blood and into the cell. When you have high blood glucose, what it is that your sugar concentration here is high. Well, what do you have to do? You have to get it out of the blood. Where does it go? Into the cell. So the bloodstream is just one component of your body. There's cells, the living cells, those things that are on the other side of that barrier, that membrane. We have to cross it. Now these things are charged, right? Because they're dissolved in water. We know one thing. They're either charged or they're what? Polar. Either they're polar or charged. What do we know about the center of the membrane? The center of the cell, you're right, is made of water. So there's water here, there's water there. But what's in the center of the membrane? Lipids. And what are lipids? Hydrophobic. They're nonpolar. So are these things going to get past that layer? No. That's the point. That's what allows them to be separate. That's what allows each of these spaces to be separate. Remember that conversation? That the membranes act as a separator, right? So that's what allows this cell to be different from this cell, to be different from what's in here. So each concentration can be different. Why? Because this membrane doesn't let it through. So what makes it semi-permeable? Somebody already said it. How do we get this stuff across this membrane? We have the transport proteins, is correct. So when we zoom in on this, we have to have these proteins in the membrane that allow, and we know what they look like, right? We have channel proteins. At this point, everybody should be able at least to partially draw a channel protein, right? Real easy. If we cross-section it, cutting it across. And we know that if this membrane is green, then we know this is all green here, right? This is all green here. And we know that if this is all blue here, then let me do this way. If we know this is all blue, then we know this whole thing is blue all the way up to there, right? And we know this at this point, I really do hope that at this point, everybody knows that this center is also blue. So then that allows anything dissolved in this, any sodium ion, let's say, to do what?
To get through.
To get through. And both ways, right? So the sodium gets through. And then we can also have a receptor, the transport protein, that's that weird one that could maybe do something like this. Maybe it fits a sugar molecule, right? And that's going to let the sugar in this way, right? Because sugars are big. Sugars are big and they're charged. They're polar, at least, and charged. And these are small, but what? Charged. So they have to have some kind of carrier to let them through. So that's fine, but I guess the question is then what lets them come through the membrane? What is it that's letting them get through that membrane, right? What makes it move? There's this stuff floating around here, and we got the doorway, right? We know the doors in the membrane are these proteins, right? A bunch of you said it already. But what makes them move? Like if I open a door, the bell rings, you get up and you move out the door, right? Does that make sense? Right? The fire alarm goes off. What do? We get up, we walk out the door. All of us will evacuate the room, right? But what lets these particles, these particles don't have brains, they don't have motors.
They trying to get to something.
Then are they? Yeah. That's right. Excellent. Somebody's been doing reading. Yeah, it's entropy. It's actually what happens is that every molecule in the universe is vibrating. So when you look at something under a microscope, we will soon look at water underneath a microscope, little things floating. What you're going to see is you're going to see these little dots moving around in every direction randomly. They're just going to be randomly moving. We call it Brownian movement after the person who discovered it. And it looked like they were alive. And when you look at them underneath the microscope, they look like they're moving. Like if something's moving, what do we think? They're alive. Unless there's some gravity or something, we don't expect non-living things to move. But what the truth is that there's constant movement all the time. Everything's moving. And the only time things stop moving is at absolute zero. Other than that, you're moving, I'm moving, we're vibrating, constantly vibrating. All our atoms, all our molecules. In fact, an MRI takes advantage of that. It moves nuclei, shakes nuclei up and releases energy, and that's what we pick up on an MRI. So what we're talking about is this random movement. So and by the way, there's another thing that I need you to know, another one of these things you have to memorize and really think about and try to apply it. Movement in general is always from high to low. This requires no extra energy. Now I say extra because if there's movement, there's energy, right? It's when you move the opposite direction. This is true of almost anything. You could take a look at about numerous examples and you can generally be assured that movement is generally from high to low. So when you're looking at like weather patterns, it's generally from high to low. When you're looking at any kind of movement that doesn't require any extra energy, it's going to be from high to low. When something's rolling, does it roll uphill by itself? No, from high to low, right? Everything in general moves from high to low. So that's just kind of a pretty standard concept. Now, if you have this membrane, it only has one little opening, and you have all this really high concentrate, and everything's moving all the time, okay? And you have a lot over here. Oh, man. And you have a lot of them here. On this side. It's a lot of them. But on this side, there's not that many. And you have this little opening here in the center. And you have random movement, just random movement. In which direction is this in, let's say, fast forward in a couple hours, what's going to happen? Yeah.
The ones on the left will move to the right side.
The stuff on the left will go to the right. Why is the stuff on the left going to the right?
Because it moves higher.
Because that's right, because things move high to low. But do you understand, can you see for just a second, can you see that the reason things move from high to just randomly, right? This doesn't require any extra energy. If things are constantly moving, they're bumping into each other, right? That just randomly, these are going to move over here because there's more stuff over here than there is over here. Does that make sense?
Yeah.
So things move from high to low. That's it. Just because of the random nature of it, over time, where there's a high concentration of something, this is high concentration. There's only a few in the same amount of volume on this side. This is high, and this is low. Things move from high to low. This is a standard. This is called diffusion. That's all it is. That's what diffusion is. Things moving from high to low with no extra energy. There's a couple of good examples of this that you know of every day that's in everyday life. One's disgusting. The other one is, I think, as equally as disgusting, though somebody would argue with me. If somebody's in the back corner of the room and they fart, they do a silent fart, eventually someone over here is going to do what? Smell it. How is it if someone over there in that corner of the room can release a gas, and then all of a sudden, all the way over here on this side of the room, they can smell it? Why? High concentration over there, low over here, so the molecules are going to move from there to here. They're going to spread out from high to low. They're going to move in every direction from high to low. Also, that explains why it's so strong over there and less strong over here, right? Because there's going to be what we call a concentration gradient. This is going to become very important very soon. So it's going to create a concentration gradient until you get to this, what we call equilibrium, and we'll talk about that in just a second. But, well, maybe not a second, but soon. So it's going to move from high to low, but it's not going to be consistent, right? Over time, what you'll get is high, right? And then, so there'll be a lot, and then there'll be less, and then there'll be less concentrated, and then less concentrated, and then less concentrated, and then less concentrated until you get, right? So you go from high to low, right? From high to low. As you move from high to low, you get this is called a concentration gradient. Is that clear? That's what we mean by concentration gradient. You're going to see that a lot when we start to talk about cellular respiration, photosynthesis. It's called a gradient. So we go from high to low, from high to low. So we call that diffusion, and that movement and the creation. That's why, again, when someone farts over here, and that's how bloodhounds follow your scent. Bloodhounds, if they smell, if you have a bloodhound, you're running away. We can give a bloodhound a T-shirt that has your smell on it and tell it to follow you, and they'll start following you. It'll start moving in the direction you're moving. Why? Because it's going the opposite direction. It has low concentration where you're far away, and where you're close. When it gets closer to you, what does the concentration get? Higher and higher until it's at you, right? So a bloodhound can smell the difference. You can smell the difference too. You know if you wanted to, and you want to know who farted, you could follow the strength of the smell, right? And it's you know, or something like that. But the other, a better example, I guess, is less disgusting, but in my opinion, just because I have to deal with it more often, is equally disgusting, is cologne. Boys and cologne. Boys seem to think that, and boys specifically, not men generally, but sometimes men, boys think that the more cologne they use, the better. Especially the cheaper stuff. The cheaper stuff is like, the reason it's so horrible is because it's so strong, and they pour it on, right? And what'll happen is, actually the better colognes last longer, they release slower, right? The cheaper stuff releases its smell a lot and very quickly, right? So anyways, and then boys are constantly moving around and getting hot, and so when they get hot, it releases it even more. And so they walk in the room and your eyes start to tear up because of how concentrated the molecules are in the air. And at least that's what happens to me. And some people actually react to that, so you gotta be careful. So anyways, that high concentration cologne, you can, if it smells, you know, like somebody's wearing, what's a cologne that bothers you? Ladies, Axe. Okay, so somebody wants to smell Axe.
Body spray.
So it's a body spray, but pretty much the same thing. And that's another thing. Guys think that instead of going to the bathroom and just washing out their pits with some paper towels, they spray Axe on and they think that fixes things. It doesn't. It just mixes the smells and makes it worse. And so girls and boys, all of us, we can follow you just by, like a bloodhound does. We can say, oh, it smells bad here, but it smells worse here. It smells even worse over here. It smells even worse over here. Oh, there you are. What's wrong with you? All right. So the best way is to reduce the concentration, by the way, just a clear hygiene message. Just go to the restroom, some paper towels and soap, and just rinse out your pits. All right? It's really easy. Yeah.
So you basically said, like, from wherever, like, whatever it starts at a high concentration, then as it continues to travel farther away.
Perfect. That's exactly right. It always moves from high to low, if there's no extra energy involved. So when you have, and that works out perfect for life.
I got a question.
Yeah.
So it disperses once it gets to low concentration, or?
It keeps moving. Gases keep moving in every direction, all the time, forever. If you release a hydrogen gas here by, I don't know how fast, but it would move very quickly, fill out the whole, it goes in, that's why the atmosphere is the way it is. You have the gases distribute evenly as quickly as they can. All right, yeah.
Can you explain the definition of gradient?
For what?
Gradient.
Gradient just means going where you see a high concentration of it, and you see a low, but see how it gets less and less and less and less?
Okay.
That is the gradient. The gradient is the various changes in concentration across distance. Is that clear? Because it's important that you understand that. In fact, when I took an art class, they required us to kind of do.
Can you restate that definition?
Wow. It's just moving from higher concentration to low concentration, all the changes in between. All the little changes. See, high, less, least. Right? Are we clear on this? A gradient is just the movement, the changes in the case in biology. What we're worried about, concentration gradient, is a change of concentration from highest to lowest and all the changes in between, all the different values in between. Are we good with that definition? Look at it. It's right in front of you. Right? Okay, so if we have a membrane and we have, let's go ahead and draw this out. We have this membrane and there's a small hole in it. And we have, let's say, 200 grams per liter, concentration 200 grams per liter here, and only 50 grams per liter here. In which direction is this going to flow?
Right.
It's going to go from left to right. See how easy that is? This part, diffusion, is easy. Diffusion is always moving from high to low. That is easy. So be clear on this. There's going to be 4 different words that each one's going to be much different. All right? So concentration, diffusion is just from high to low. That's it. No extra energy. There's energy involved, obviously, right? Because it's moving, but there's no extra energy. It's just the random movement of molecules, the kinetic energy of the material. And of course, the warmer it is, the higher the kinetic energy, so the quicker things get. By the way, it's going to keep going, right? Let's think about something else, because this is a good time to discuss this. I'm going to go ahead and discuss it. It's going to go ahead and keep changing, right? So it's going to go from this high, right, from stage 1 to stage 2. I can't stand when it does this. So from stage 2, oh my goodness. So if we have this membrane, this thing always groups things I don't want it to group. So if we have this concentration on one side, right, over time, what's going to happen? This stuff's going to do what? Move over there, right? So eventually you're going to have, oops, let me stick with blue. You're going to have this, right? It used to be what we saw a minute ago, right? And then over time, you have less of these, right? And more on this side. Until what? What do you think is going to happen?
Until it reaches equilibrium.
Until it reaches equilibrium. Until they reach about the same concentration on both sides. Until you reach the same. That's what same means what?
Equal.
Equal, right? Equilibrium. So equilibrium is when both sides are equal. Both sides have equal what? Concentration. So they're going to keep moving till both sides have equal concentration. Easy, right?
Mm-hmm.
Real easy.
So once you have the same amount of concentration in the cell and in the bloodstream, it stops?
Not quite. It's a different. It's good thinking. You're thinking well. The story's more complicated. We're talking about the basic ideas right now. So read the chapter, guys. So equilibrium goes out to about equal, but does the movement stop? These things are always moving, right? So eventually you're going to get one of these goes this way. Nobody told you that it's only going to move in one direction. I said randomly you're going to get things moving in this direction net, right? Most of the things are going to move in this direction. But if this is all random, as for every one that goes this, if you got 100 to go this way, what's going to happen? Is anything stopping these from going back? No. So every time you get one going this, if you have a lot, if you have this situation where you have a lot of these on this side, right? You have a lot of these on this side, then randomly, you're going to get a lot of these going towards the right. Only a few of them are going to go to the left because there's less of them, right? But if you're talking about when you're at equilibrium, for every one that goes to the right, what do you get? One that goes to the left. And because you're getting one going to the they keep going in that what we call dynamic equilibrium. As you saw here, this is dynamic. Everyone to the right there's one that goes to the left because they're close to equal. And you keep equilibrium, you keep the balance, the concentration same on both sides, but it's constantly changing. Well, what happens when the ions cannot go through? What happens when the solute cannot pass, but water can? We call it osmosis, and that's what we'll be covering tomorrow. And simple diffusion is just simply this idea of things moving from high to low. That's not hard. I think everybody, so far, it seems like everybody says they understand. I don't know if some of you are holding back, but it's not if you understand, or at least you say you do. But with osmosis is what happens when the solute cannot move because there is no opening for the solute. The membrane allows water through because it has these things called porins, these little openings that allow water through. But these openings are either too small or something's happening. The reason is irrelevant. Something's happening that only water can get through, H2O can get through in both directions, right? But the solute can't. The solute cannot get through. That's a no-go. So it's blocked. Well, something really weird happens. This is almost anti-intuitive, but it still is based on this idea of random movement. I have to say, it's still based on random movement. However, I'll just say this. What ends up happening, I don't know why anybody's putting anything away, because we're still kind of trying to get through this. And I know it's 11:53, but we still got like 4 minutes left in class. It turns out, let me go ahead and draw this, because this is the kind of the coolest experiment I like to think about. It's the first U-tube. It's literally a U-tube. And I don't know why. I know that YouTube is based on the idea that TV used to be a tube, so I guess. So they put this membrane here. You have this membrane. And then you put water. Let's put the membrane in red. There's some solvent. And initially in the tube, the solvents are about equal, but then you add salt on this side. And this membrane is not permeable to salt, right? Not permeable. What does that mean? What does permeable mean? It can't. Permeable means it can go through. Not permeable means it's not able to go through. So here on this side you put sodium ion and it can't get through. And there's 10 molar. You don't know what molar is yet, so let's just say 10 grams per liter salt concentration on this side. And here you got 5 grams per liter of salt concentration on this side. Well, what's going to happen? You have a concentration difference. The salt can't move. You can't. If the salt can move, then all you're going to get is what? What's going to happen if the salt can move? You'll get dynamic equilibrium. What's going to move? The from here to here. It'll move right. The salt will move from here to here until you get somewhere in between 10 and 5, right? We're all good with that? You don't have to figure out what the number is. It's going to move from left to right until you get equilibrium, dynamic equilibrium. There's going to be movement in both directions, but net movement will be towards the right. We get that. But if it's not permeable, then the weirdest thing is going to happen. I think it's weird. I don't know if you think it's weird. The water is going to move, and the water is going to move. In which side is the water going to move? To the right or to the left?
Left.
To the left, because there's more salt over there, and it's gonna move until the right is higher concentration and left is lower until you get something that's in between, until you get your equilibrium. You're gonna reach equilibrium one way or the other. It's gonna happen either with osmosis or diffusion. So instead of 10, maybe it's, I don't know, I'm gonna say 6 on both sides. I don't know if that's true. You can figure it out, but I'm just making it up as I go here. So are we clear? So we literally have this water going up and this water going down so that this becomes higher concentration salt, this becomes a lower concentration salt until you reach some dynamic equilibrium. This has real serious consequences to your cells. Serious consequences to your cells. This is why, pay attention, because this is why when you eat too many of those sunflower seeds, those salty sunflower seeds, the inside of your mouth starts to slough off. You get that skin coming off the side of your mouth. This is why when you eat super salty things, the inside of your mouth kind of peels off. Because your cells blow up or shrivel up, depending on the constant whether the water's going into the cell or out of the cell. This is also why your hands shrivel up in water when you're bathing. This is why your plants, when you don't water them enough, they do this. They start to wilt. All of this in life is based on this idea of osmosis, a very important idea. All right, read about it. Make sure you get the chapter work done. See you tomorrow. We'll finish this tomorrow. And say this, that when we're talking about osmosis, we're talking about the solvent moving, right? The solvent, water is moving. Water is moving. So when we're talking about water moving, not the solute. This has real serious implications on cells. So let's talk about a little bit about what that means for cells. And we'll talk more about it tomorrow. So when we're talking about cells and not a battery, that was a discussion we had earlier. So if we have this cell, what happens if you take a cell, and by the way, this is why when you eat a lot of salt, the inside of your mouth starts to peel off.
Yeah.
So you ever had that happen? You eat too much salt, it burns and it's salt, and the skin kind of falls off. And you ever sit in a bathtub and get all wrinkly?
Yeah.
And yeah, pool it happens less often, but it does happen. So you get all wrinkly. It's like it's upsetting to some people. I don't mind it, but some people get upset. And why a plant droops. You ever have a plant that starts to wilt, starts to go, oh my. So that's all because of this. So what happens is you take this beaker and you put this cell in a beaker, and in the water, if the cell is, let's say I'm just going to put numbers, okay? And I'm going to say 10 inside the cell. The cell is 10 milligrams per liter, and outside the cell, I'm going to say the solution is put in a solution that is, let's call it 20 milligrams per liter of salt, or something that's not permeable to the membrane, right? Doesn't get through. So the inside is 10, the outside's 20. If the stuff could move, in which direction would the stuff move? High to low. Right? The solute, if it could move, the solute would move, but the solute can't move. So the water's going to move in what direction? The opposite direction.
Yeah.
So the opposite direction, so it could dilute the other side. So the water moves in this direction, right? But what does that do to the cell? The cell becomes what? If we go ahead and redraw this with the new cell. What does a new cell look like once they're close to equal?
Are they combined together? Will they join?
What happens to the cell? One single cell. No, it won't dissolve. It'll do this. All the water's out of it, isn't it?
Right.
It'll shrivel up.
Oh, because it's going, oh.
It'll shrivel.
Oh.
I don't know how to spell shrivel. Is that spelled right?
I believe so.
Somebody double check it. It would shrivel up. Could somebody double check it?
Mendoza, who's the real life example of that?
I just gave it to you. Thank you. All right, so the salt in your mouth, right? Is exact, huh? EL, thank you very much. Do we all understand that? It's that example I just gave you. Where, what would happen though, what happens if the opposite were true? What if I took that cell and I put it in, and it was 20 inside and 10 outside? Now what's going to happen to that cell? In which direction is the water going to move now? Now, normally the solute would move from inside to out, right? But it's going to move the opposite of that, so it's going to move in, right? What's going to happen to?
So it's
Gonna get bigger.
It's going to get bigger, right? So the cell's actually going to do what? Swell. It could blow up. It could actually explode, right? You're right. Until both sides, 15 and 15, let's say. I don't know. I'm making that number up. And of course, this side would be 15 and 15. So in both cases, they're now 15 each. But one, the cell shriveled. The other one, the cell swelled. So that is a big problem for cells, right? Now with humans and animals, what we do is we have all kinds of mechanisms to stop that from happening. What do plants have that help them stop this from happening to their cells? They don't want their cells to explode.
They have a cell wall.
They have a cell wall. That's it. You got it. You got it. That's why cells and bacteria have cell walls, because they don't have feet that can move them. So if they have a cell wall and they have this plasma membrane on the inside and it swells up because it's in hypotonics, that's why giving a plant a lot of water is good for the plant. The plant loves it. The plant cell does not have to worry about blowing up, does it? It doesn't, because it has a central vacuole, first of all. And the second thing, it has this thing called the cell wall. And so it fills up the cell wall. And because it's all filled up, the plant stands up straight. And you have the flower with the leaves, and everybody's happy. When the opposite's occurring and the cell loses too much water, the poor little plant, well, ultimately it'll die, but it wilts. There's this horrible drawing of a plant. All plants on the planet, forgive me. As the plant loses too much water, but the cell doesn't die completely. If there's a resistance to that, because there's a cell wall holds it together, it doesn't collapse altogether. It shrivels up, but it doesn't shrivel up completely because it's still attached to the cell wall. And so, of course, plant cells prefer it this way. Animal cells have a lot less structure to support them, but of course if we have too much water, we just drink less of it, or we get out of the pool or whatever, so we don't shrivel up completely, right? We get out of the pool, and we're multicellular organisms, so we can transport the liquids in different places. So as water moves from one tissue, it can flow into the other. Plants don't have the ability to move, so they depend on that cell wall to hold it together. Are we all good then?
Yeah.
So that's the kind of concepts we'll be talking about for the rest of tomorrow. Be ready to discuss osmosis and facilitate diffusion and all the different scenarios that are in the chapter reading. Put up your chairs and clean up your area, and then when the bell rings, have a great day.